Let's now move to a discussion on elastic stiffness and compliance tensors. How are particle displacement and deformation related to the medium properties? Physical properties of the medium are weight, or density, and rigidity, that is, elastic constants which describe resistance to deformation. Up to this point, we have introduced mathematical descriptions of stress, displacement, and strain. To complete this list of all physical quantities entering into wave propagation theory, we will need to introduce mass density and elastic properties, which characterize individual rock formations, basically resistance to deformation. Here are the detailed plans of how we will proceed with this lecture. First, we'll recall subscript notation and summation convention. We'll then discuss stress-strain relationships, also known as Hooke's law for small deformations. Understanding this relationship is the main learning outcome of this lecture. We'll then move to isotropic and anisotropic medium descriptions, which are associated with specific stress-strain relationships. Lastly, we will discuss Poisson ratio, bulk modulus, and Young modulus, which are also specific elastic moduli associated with particular cases of stress-strain relationships. For reasons which will become evident in our definition of elastic constants, we introduce the subscript notation for vectors and tensors, and the summation. In subscript notation, a vector A can be denoted by AI. That is as follows. Here, lowercase Latin subscripts, for example I, are assigned the values 1, 2, and 3. Here is another example of subscript notation. Here we are dealing with a two-rank tensor, tau ij. This notation permits us to write many of the formulae in seismology in a much shorter form than would otherwise be possible, making these formulae easier to remember and to understand once the notation is learned. Here is an additional example of subscript notation, which includes the Kronecker symbol. That is, delta ij is 0 when I is different than j, and delta ij is 1 when I is equal to j. Notice how compact the description of stress tensor in non-viscous fluid is. Many of our formulae, including the stress-strain relationships, require a summation over all values of the subscripts. The summation convention states that whenever the same letter subscript occurs twice in a term, that subscript is to be given all possible values and the results added. For example, the scalar product can be written as follows. The sum symbol may then be omitted because the repeated subscript indicates the summation. Here is another example. We omitted the sum symbol over j. The subscript j is repeated here, and therefore it indicates summations over j. However, there is no summation over I. Remember that an uppercase Latin subscript here takes the value from 1 to 6, whereas a lowercase Latin subscript takes the values from 1 to 3. One more example. Here, tau ij is equal to Cijkl multiplied by EKL. We omitted the two sum symbols. The subscripts K and L are repeated here, and therefore they indicate summations over the subscripts K and L. However, there is no summation over the subscripts I or J. So the summation convention dispenses with writing summation signs, leaving the summation implicit. Any repeated index symbol is summed over. If the index I is used twice in a given term of a tensor expression, it means that the term is to be summed for all I. Several distinct pairs of indices may be summed this way. Let me repeat this, as they are the key conclusions of summation convention. The summation convention dispenses with writing summation signs, leaving the summation implicit. Any repeated index symbol is summed over. If the index I is used twice in a given term of a tensor expression, it means that the term is to be summed for all I. Several distinct pairs of indices may be summed this way. We're now discussing stress-strain relationships, also known as Hooke's law for small deformations. Again, understanding this relationship is the main learning outcome of this lecture. In an elastic body, stress depends only on the strain, and vice versa. As discussed in the previous lecture, we are essentially considering small deformations. For small deformations, it is an experimentally observed fact that the strain in a deformed body is linearly proportional to the applied stress. That is, generalized Hooke's law. In this case, the deformation is characterized as linearly elastic. As increasing deformations are imposed, the relationship between strain and stress becomes increasingly nonlinear. But the body still returns to its original state when the stress is removed. In this case, the deformation is characterized as nonlinearly elastic. If, however, the strain is increased past a certain limit, typically in the range 10 to the negative 4 power to 10 to the negative 3 power for relatively rigid materials, the deformation is no longer elastic. Beyond this elastic limit, the medium deforms permanently, that is, plastic deformation, and ultimately fractures, that is, materials are no longer elastic. Ordinarily, the plastic deformation region is not of interest in the study of seismology. For small deformations, we will limit our discussion to linear elasticity, which is the yellow area in this figure. So here we will focus on small deformations in the case in which the strain in a deformed body is linearly proportional to the applied stress, which again is generalized Hooke's law. Let's now turn to the linear relationships between strains and stresses. Before we immerse in strain-stress relations, Let's recall the linear relationship between scalars that most people are familiar with. This linear relationship is shown here in blue. The constant A may be a number, a parameter, or even a nonlinear function of parameters. And the distinction between variables and parameters may depend on the problem. Now we consider vectors instead of scalars. We have multiple constants. For a linear relationship between two 6-component vectors, such as stress and strain tensors in abbreviated notations, we have 36 constants. Remember that the summation convention is used here. The constants of proportionality, Cij, are known as elastic moduli or stiffness constants. They define the elastic properties of a medium, more particularly its resistance to deformation. The thermodynamics tells us that the stiffness tensor is symmetric. This symmetry implies that we actually have 21 stiffnesses. The 21 stiffnesses are the maximum number of constants for any linearly elastic and isotropic medium. It is known as triclinic symmetry. Usually the number is much smaller than this because of additional restrictions imposed by the microscopic nature of the medium. Now we consider matrices instead of vectors. We also have multiple constants. For a linear relationship between 3x3 matrices, such as stress and strain tensors, tau ij for stresses, and EKL for strains. We have 81 constants, Cijkl, which is 3x3 by 3x3. Remember that the summation is used here. This summation is over subscripts K and L. Because of the symmetries of stress tensor, we have the following symmetry between stiffness, as you can see here. Because of the symmetries of strain tensor, we have these additional symmetries between stiffness, as you can see here. Based on thermodynamic arguments, we also have the following symmetries between stiffnesses, as you can see here. Again, these symmetries allow us to have a maximum of 21 independent stiffnesses. So we have two types of stiffness tensors: stiffness tensor of rank 2 and stiffness tensor of rank 4. The relationship between these two tensors is given here in blue. It allows us to go from the elements of one tensor to the elements of the other tensor using the subscripts equivalence table below for this relationship. Again, remember that an uppercase Latin subscript here takes the values from 1 to 6, whereas a lowercase Latin subscript takes the values from 1 to 3. Let's now turn to the inverse relationship between strains and stresses. Before we immerse in the inverse strain-stress relationship, let's recall that we can take the inverse linear relationship between scalars that most people are familiar with. Now we consider vectors instead of scalars. We have multiple constants. For an inverse linear relationship between two 6-component vectors, such as stress and strain tensors in abbreviated notations, we have 36 constants. Remember that the summation convention is used here. The constants of proportionality, Sij, are known as elastic compliances. Now we consider matrices instead of vectors. We also have multiple constants. For an inverse linear relationship between 3x3 matrices, such as stress and strain tensors, tau pq for stresses, and EKL for strains, we have 81 constants, S, KL, PQ. Remember that the summation is used here. This summation is over subscripts P and Q. Again, the strains can be expressed as linear functions of all stresses, as we can see here. In this case, the constants S, KL, PQ, called compliance constants, are measures of the deformability of the medium. The compliances take large values for easily deformed materials and small values for rigid materials. Here is the abbreviated notation of the compliance tensor. Please pay attention to the extra factors 2 and 4. These factors ensure that the compliances are inverse of stiffnesses when using these quantities as second-rank tensors. To summarize, the elastic stiffness constants or compliance constants of the most general elastic and isotropic material satisfyCijkl, which equals CKLIJ, in addition to the symmetry relation, as follows, and corresponds to only 21 independent elastic moduli, or 21 independent compliance constants. The compliances take large values for easily deformed materials and small values for rigid materials. For a given point or particle, x, at time t, the generalized Hooke's law states tau ij equals c ijkl times ekl. The constants of proportionality are known as elastic moduli, or stiffness constants. They define the elastic properties of a medium, more particularly its resistance to deformation. These constants constitute a 4-rank tensor, which is known as the stiffness tensor. Notice that the elastic moduli are assumed to be independent of time t. This is the case because we have assumed that the materials under consideration in this lecture are elastic. Anelastic materials will be discussed in future lectures. The stiffnesses and compliances are defined with respect to a certain Cartesian coordinate system. However, this system may not always be the most convenient choice of axes for solving a specific problem, and it is therefore necessary to consider how the stiffnesses and compliances may be transformed into other coordinate systems. If new rectangular Cartesian x', y', and z' axes are chosen with the same origin as the original rectangular Cartesian x, y, and z axes, the direction of each new axis can be specified by giving its direction cosines with respect to the old axes. For instance, the direction cosines between the unit vector I'1 in the x' axis of the new coordinate system and the unit vector I1 in the x-axis of the old coordinate system are A11 equals cosine theta 11, according to the definition of a scalar product, because I'1 and I1 are unit vectors. Their magnitudes are both unity. The direction cosines defining the other changes of axes are conveniently tabulated as follows, where APQ equals cosine theta PQ. A first-rank tensor or vector transforms according to this law. U' equals Aij Uj. A second-rank tensor, like the strain, transforms according to E'Ij equals Aik Ajl Ekl. The fourth-rank stiffness tensor transforms as follows. This formula is the one we use for stiffness and compliance tensors. Now it's time for a quiz. Determine missing stiffnesses in this table. Now we will talk about isotropic and anisotropic medium descriptions associated with specific cases of stress-strain relationships. Let's start by illustrating the differences in terms of wave propagation between isotropic and anisotropic media. Here are snapshots of wave propagation in a homogeneous isotropic elastic medium to the left and a homogeneous anisotropic elastic medium to the right. Notice that the speed of wave propagation in the first case, that is, the isotropic case, does not depend on direction or the axis system, whereas in the second case, that is, anisotropic case, it does. That is the difference between wave propagation in an isotropic media and in anisotropic media. In other words, for the first case, the material is characterized as isotropic. In this case, the stiffness tensor must be invariant under rotation and reflection. In the second case, the material is characterized as anisotropic. That is, its properties cause wave propagation to vary with direction. Let's watch this animation of a pressure source. The quantity displayed here is divergence. This animation may help you crystallize the notion of anisotropy. Let's take a quiz about stiffness tensor. Consider the following stiffness tensor, where delta Ij is the Kronecker delta function notation, as shown here. Construct the corresponding 6x6 matrix. Here is the answer. Pay attention to the structure of this matrix and to the number of independent parameters this matrix contains. Notice that for isotropic media, the stiffnesses must obey these conditions. C11 is equal to C22 equal to C33. C44 is equal to C55 equal to C66. C12 is equal to C13 equal to C23. In addition, C12, for example, must be equal to C11 minus 2C66. All the other stiffnesses are 0. All 5 of these conditions must be satisfied to have isotropic media. So we have just described the stiffness tensor for the case of isotropic media. Notice that isotropic media can be described by 2 parameters only, which are lambda and mu. The stiffness tensor of isotropic media is unchanged by the rotation of the coordinate systems, confirming that this stiffness tensor of isotropic media is invariant with direction. We have seen that each of the 6 independent components of stress at a point are linear functions of the 6 independent components of strain. The result is 36 elastic constants, which can be further reduced to 21 based on thermodynamic considerations. The most general anisotropic materials are described by 21 constants. Fortunately, the elastic properties for many materials and material composites in the Earth are predominantly independent of direction. Hence, the isotropic stiffness tensor is an appropriate first-order approximation of most rock formations. To conclude the answer for this isotropic case, let's observe that one can also construct the compliance tensor for isotropic media from the stiffness tensor using the definition described in the previous slides. Here is the compliance tensor of isotropic media as a 4-ranked tensor. Notice that the compliance tensor also depends only on lambda and mu, just like stiffness tensor of isotropic media. Using the definition described in the previous slides, the compliance tensor of isotropic media can be written as a 2-ranked tensor as follows. Again, notice that the compliance tensor depends only on lambda and mu, just like stiffness tensor of isotropic media. Let's take another quiz. Is this tensor shown here described anisotropic or isotropic media? Here is the answer. We have anisotropic material. This case is described by 5 parameters. The speed of wave propagation in this case depends on direction. Again, the material in this case is characterized as anisotropic. Its properties cause wave propagation to vary with direction. Here's an additional quiz. Is this stiffness tensor isotropic or anisotropic? The answer is that this stiffness tensor is anisotropic because C11 is different than C22 and so on. Although the matrices have the same zero stiffnesses as the isotropic case. Here's the next question. Is this stiffness tensor isotropic or anisotropic? The answer is that this stiffness tensor is anisotropic. Notice that C11 is equal to C22, equal to C33, and also C44 is equal to C55, equal to C66. C12 and C13 and C23 are equal. However, C12, for example, is not equal to C11 minus 2C66. So this media fails to be isotropic because it did not fulfill condition number 4. Anisotropy describes variations of the physical properties with direction at a given point. Remember that a point represents a particle. Heterogeneity describes variations of physical properties between two or more points. So anisotropy describes the physical properties of a specific point of the medium, whereas heterogeneity can be used to describe point-to-point variations in geometries or physical properties. Anisotropy and heterogeneity generally coexist. There are 4 possible scenarios: isotropic and homogeneous, isotropic and heterogeneous, anisotropic and heterogeneous, and anisotropic and homogeneous. Anisotropic and heterogeneous is found fairly commonly in seismology studies. An example would be a bed with an acoustic velocity varying in direction at any given point. If different anisotropy was observed at different points, the bed would be both anisotropic and heterogeneous. Lastly, we discuss Poisson ratio, bulk modulus, and Young modulus, which are elastic moduli associated with a particular form of stress-strain relationships. The relationships between stress and strain in the isotropic case are given here. Mu and lambda are called the Lemay parameters. Mu measures a material's resistance to shear, that is, changes in shape without changes in volume. It is positive and has a unit of stress. A typical value for rock formations is 200 kilobars. In non-viscous fluids like water, only changes in volume play a role in the stress-strain relationship. Therefore, mu equals 0. The second constant, lambda, has no single physical meaning, but it greatly simplifies Hooke's law. Let's introduce 3 new parameters: bulk modulus, or K, Poisson's ratio, or nu, and Young's modulus, or E, which have a clearer physical meaning. These parameters are often used to characterize the elastic properties of rock formations. Let's start with Poisson's ratio. Consider a purely compressional stress applied in the x direction. In other words, tau xx is applied and all other stress components are 0. The stress strain, that is, Hooke's law, for isotropic media becomes the following. Then we can define the Poisson's ratio as follows. Remember that the Poisson's ratio here is defined as nu. Poisson's ratio is dimensionless and has a maximum value of 0.5 for a non-viscous fluid. That is, when the shear modulus equals 0. There is no shear resistance. If the smallest value of Poisson's ratio is 0, we have infinite shear resistance. Most earth materials have a Poisson's ratio of between 0.2 and 0.4. For typical igneous rocks, such as granite, Poisson's ratio is approximately 0.25, and for sedimentary rocks, Poisson's ratio is between 0.2 and 0.4. Let's now talk about the bulk modulus, or incompressibility. We basically subject a solid to a uniform hydrostatic pressure. That is, all of the normal stresses are equal to minus P, while the shear stresses are all zeros. The first three equations of the stress-strain relationship, that is, the relationships between normal strains and normal stresses, allow us to deduce the normal strains. EXX, EYY, and EZZ. Notice that all these strains are identical, and we define them as volumetric strain and denote them as uppercase theta. So we can deduce the bulk modulus as the ratio of normal stress, that is pressure, P over the normal strain, which is uppercase theta. K is called the bulk modulus, also referred to as incompressibility. It is the material resistance to a change in volume when it is subject to a load, and therefore it must be positive. As a material becomes more rigid, the bulk modulus increases. Since shear modulus equals 0 and Poisson's ratio equals 0.5 for all non-viscous fluids, they cannot be used to differentiate between fluids. However, the bulk modulus K can be used because it varies with the type of fluid. Let's now talk about the Young's modulus. The Young's modulus, also known as the modulus of elasticity, is the measurement of the resistance of a solid to a change in its length. It is named after Thomas Young, who introduced it in the 19th century. Consider a purely compressional stress applied in the x direction, in which all stress components are 0 except tau xx, just like we did for the derivation of the Poisson's ratio. However, this time we are not interested in the ratio of strains, but rather in the ratio of the longitudinal stress tau xx to the corresponding longitudinal strain EXX produced by the stress tau xx. The Young's modulus in Pascal is as follows. Note that the shear modulus can be expressed in terms of the Young's modulus and Poisson's ratio as follows. Since shear modulus and Poisson's ratio are always positive, it follows that the Young's modulus, E, is always positive. In summary, Hooke's law for solids and liquids are given here. We have now concluded our description of stiffness and compliance tensors. When we return, we will describe wave equations and external force sources. Thank you.